Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a Calculus 1 lecture. I hope you enjoy it. This is chapter 4.5, which is limits at infinity. All right, so first, let's get a formal definition of a limit at infinity. All right. Formal definition. Let L be a real number. All right. The statement, um, so the statement, the limit as x goes to infinity of f of x equals L means that for each epsilon greater than 0, there exists an m greater than 0 such that the absolute value of f of x minus L is less than epsilon whenever x is greater than m. All right. I'll explain what that means in a second, visually. But before that, we have a similar statement. The statement, the limit as x approaches negative infinity of f of x equals L, means that for each epsilon greater than 0, there exists an n less than 0, and I'll use a capital N less than 0, such that absolute value, well, actually the rest of that's the same almost, such that the absolute value of x minus L is less than epsilon whenever x is less than n. All right, so let's get a visual to these statements. All right, so here we go. The visual for number 1. All right, let's say that we have our x and y axis. Right, and we had a function that looks something like this. Right? In here, well, we're gonna say here's L, and I'll do it in blue. Here's our height L. And if we have some epsilon distance here, well, let's do it this way. And on both sides of that, so that's epsilon, all right? After some specific point around here, right, around here, if here's M, all the x's after this break, after this point, are all within epsilon distance of our limit, of our L. And that's what that's saying. I mean that after a certain point, everything, like all the y values, are within epsilon distance of this line L. What this actually um, is essentially called a horizontal asymptote, right? And by the way, the visual for the second one over here is the same exact idea, but now it's facing negative infinity. Now, let's get an actual definition here. So, definition for a horizontal asymptote. So, the line L, so the line y equals L, is a horizontal asymptote, and that's how I'll abbreviate horizontal asymptote, HA, of the graph of f when either the limit as x goes to infinity of f of x equals L, or the limit as x goes to infinity, negative infinity, excuse me, of f of x equals L, right? So essentially here what you're saying, if the function is going to have a horizontal asymptote, it's going to happen when the limit is going to infinity or towards negative infinity. So let's see how to find these kinds of limits. So theorem. So this is for limits at infinity. And here's what the theorem says. If r is greater than 0, so if r is greater than 0 and r is rational, all right, so it needs to be a fraction, and c is a real number, so any real number, then the limit as x approaches infinity of c over x to the r is equal to 0. The same thing applies when the limit is going to negative infinity. All right, and in here we always assume that x to the r is defined for x being less than 0, right? So in other words, we want to make sure that the denominator is not 0. All right, so now that's for this kind of limit where we have a constant over x to a power, right? Now the second scenario, if I have the limit as x approaches negative infinity of e to the x, that equals 0. Similarly, the limit as x approaches positive infinity of e to the negative x is also equal to 0. Um, and here, it's easy to try to visualize this, why this would be true, right? If I have e to the x, this is e to the x. So as x goes to negative infinity, the function approaches 0. Similarly, over here, e to the negative x looks like that, right? So same exact idea, but now going towards the other side. All right, so as x goes to infinity, this function goes to 0. For the first limit, for this one up here, this should also make sense, right? Because we have a constant divided by a huge number. Think of it as if I had, I don't know, a slice of pizza, and I'm dividing it by infinitely many people. How much pizza does each person get? Well, essentially, no pizza, right? Because we're dividing it by a huge number of people. So that's what's going on here. A constant number divided by a huge number, it ends up becoming closer and closer to 0. All right, so let's find some limits. So let's say that we have the limit as x goes to infinity of 4 plus 3 over x. All right, now in here, as x is going to infinity, this piece right here goes to 0, right? That was scenario 1 up here, a constant over x to a power. So that goes to 0. So what we actually end up with here is just 4. Right? Next example. If I have the limit as x goes to infinity of 2 minus 5e to the negative x. All right, well, excuse me, from here, right away as x is going to infinity, I see that this value goes to 0. So this right here is going to go to 0. meaning that I have 2 minus 0, which is just 2. All right. Let's complicate this a bit. If I have limit as x goes to infinity of well, let's do negative infinity of 2x minus 1 over 3x plus 2. All right. I can't I can't just plug in infinity here, right? Because if I plug in infinity, or negative infinity, excuse me, I end up with negative 2 infinity on the top, and essentially just negative infinity. And on the bottom, negative 3 infinity, essentially just negative infinity. So I end up with negative infinity over negative infinity. Well, what is that supposed to be? We can't. That right there is called indeterminate, all right? Because that's not an actual, you can't actually divide infinities. Infinities are not actual numbers. It's just the representation or the idea that numbers get huge, but it's not any actual number, so you can't just divide infinities. So, well, what can we do here? Well, let's see. What we can say now is, well, there's two things we're allowed to do to any math problem. Those two things are add 0 and multiply by 1. In this case, we're going to multiply by 1. And the one that we're going to multiply is going to be 1 over x over 1 over x. And why did I choose 1 over x? Well, in here I chose 1 over x because x is the highest power, so that to the first power is the highest power of the denominator. So that's what I want to do. I want to divide by the highest power of x on both the top and the bottom. And what we get now is we end up with the limit as x goes to negative infinity of 2 minus 1 over x over 3 plus 2 over x. And now, as x goes to negative infinity, this piece right here goes to 0, that piece goes to 0, so overall, we end up with just 2/3. Right? Let's look at a similar example to this. D. Let's take the limit as x goes to negative infinity of, let's do something very similar to this. 2x minus 1 over 3x squared plus 2. All right. Notice that it's essentially the same idea. I just changed it into x squared on the bottom. Well, in here we're going to start in the same exact way, right? Because if I were to just plug in infinity, I end up with infinity on the top, infinity on the bottom. That's indeterminate. So we need to manipulate this. And the way we're gonna manipulate this is, well, again, we're going to multiply by 1. And we've got 2x minus 1 over 3x squared plus 2. And the one that we're going to multiply by is going to be 1 over x squared over 1 over x squared. And the reason I'm using 1 over x squared is because that is the highest power of the denominator. And at that point, well, what does that give us? That gives us, well, the limit as x approaches negative infinity of 2 over x minus 1 over x squared over 3 plus 2 over x squared. And now, as we take the limit as x goes to infinity there, well, this right here goes to 0, that right there goes to 0, that goes to 0, so we end up with 0 over 3, which is just 0, right? Next one, E. And again, we're going to do a very similar one. Let's say it has the limit as x approaches negative infinity of 2x squared minus 1 over 3x plus 2, all right? So let's see. In here, if I let negative x go to infinity, I once again end up with infinity over infinity, right? And in here, well, actually negative infinity on the bottom, right? And in here, that is in indeterminate form. Oh, actually, negative infinity on the top up here. Sorry. But anyway, back to this problem. And here we end up with a determinate form. So what we say here is we're going to have the limit as x goes to negative infinity of 2x squared minus 1 over 3x plus 2. And again, we're going to multiply by 1. And as before, the one we're going to multiply is going to be determined by the denominator. So in here, I'm going to divide by 1 over x, right? Determined by the denominator. So what does that give us? Well, we end up with the limit as x approaches negative infinity of 2x minus 1 over x over 3 minus 2 over x. And at that point, well, what do we get? This goes to 0, right, as x goes to negative infinity. This also goes to 0, but this goes to infinity. So essentially what we have here is infinity minus 0 over 3 minus 0. That's just infinity, right? Infinity divided by 3, infinity. So let's see essentially what we found here. So, well, this does not exist. And let's revisit all these first 5 problems. Recall that I said that what this was finding was horizontal asymptotes, right? So for this function, 4 plus 3 over x, we've got a horizontal asymptote of 4. For this one, we've got a horizontal asymptote of 2, so on and so forth. In example C, we've got a horizontal asymptote of 2/3. In D, we end up with a horizontal asymptote of 0. In E, we end up with no horizontal asymptote because it's not an actual value. All right, that value, that limit didn't exist. All right, so that's something you want to keep in mind. Now, let's look at these last 3 scenarios, C, D, and E, and let's look at the degrees here. Notice that in here, x and x, they were both of the same degree, and our final answer was just 2/3. Notice that in the next scenario, in here, the degree on bottom was bigger, and our final answer was 0. And in the last scenario here, the degree on top was bigger, and there was no horizontal asymptote. That should remind you of this rule from pre-calc regarding horizontal asymptotes. So maybe I'll make this as a note, and I'll do it in yellow. Note on horizontal asymptotes. Given that y is equal to, actually let's write it this way. Given that f of x is equal to n of x over d of x, where n of x is just some polynomial, and d of x is some other polynomial of different degree, right? Well, we have 3 scenarios. So scenario number 1 was that if the degree on top is bigger than degree on bottom, then there was no horizontal asymptote. If the degree on top was equal to the degree on bottom, then what we found here was that the horizontal asymptote was just the line y equals a sub n over b over m. And if the degree on bottom, if the degree on top is less than the degree on bottom, the horizontal asymptote was a line y equals 0. Right? So this was something from pre-calc. And where does this come from? Well, essentially this idea of taking the limit as x goes to infinity or negative infinity of a function. All right. All right. So now, what was that? E, F. So let's see. I have the limit as x approaches infinity of 1 over 1 plus e to the negative x. All right. Well, let's look at what I wrote up here. Here, we have these two limits. As x goes to negative infinity of e to the x, that's 0. And as x goes to positive infinity of e to the negative x, that's 0. All right? So let's keep those in mind. X is going to positive infinity. Well, let me actually just remind you what those limits were. The limit as x goes to positive infinity of e to the negative x is 0, and the limit as x goes to negative infinity of e to the x equals 0. All right, so in here, what do we have? We're going to infinity, and we're involved in e to the negative x. There you go. Good. We can use this. We end up with 0. So what I end up with is 1 over 1 plus 0, which is 1. Okay. Now let's look at the limit as x goes to negative infinity of that same exact function, 1 over 1 plus e to the negative x. Notice here that now we're going to negative infinity, and the rule that I had for powers of e was e to the positive x, not e to the negative x. Similarly, the one that I had for e to the negative x was going to positive infinity, but we're not going to positive infinity. So as written, we can't use either one of these. So we have to manipulate this. So how are we going to manipulate this? Well, let's see. We can always add 0 and multiply it by 1. In this case, I'm going to multiply it by 1. And in this case, I'm going to use e to the x over e to the x. Why am I using e to the x? Well, I see that I want to make the limit go to negative infinity. So I'm going to use what I need from there, e to the x. And well, what does that give us? That gives us now the limit as x goes to negative infinity of e to the x over e to the x times 1, e to the x. E to the x times e to the negative x, that's 1, right? At the exponents, negative x plus x is 0, so e to the 0 is 1. And now we can actually go ahead and use this. Excuse me, this down here, right? Because we have e to the positive x now. So at this point we say, well, as x is going to negative infinity, our numerator here is going to 0. This piece here also going to 0, so we get 0 over 0 plus 1, which is just 0. All right. Now, notice something that these two examples show us. Remember that the limit as x goes to infinity or negative infinity, they represent horizontal asymptotes if we get an actual limit. We did get an actual limit on both scenarios of the same function, right? 1 over 1 plus e to the negative x. So what we found here is that the function, so I'll make a note here. Note, f of x equals 1 over 1 plus e to the negative x has two horizontal asymptotes, all right? And in fact, that's the most amount of horizontal asymptotes you can have. You can have infinitely many vertical asymptotes, right? For example, tangent of x, that has infinitely many vertical asymptotes. But horizontal asymptotes, at most you can have two. One is equal as x goes to positive infinity, and the other as x goes to negative infinity. All right, so I'll just draw what this function looks like so you have an idea, right? And it looks something like this. We have a horizontal asymptote going to 0 as x went to negative infinity, and then it was going to 1 as it went to positive infinity. So we're going to have this vertical asymptote there at y equals 1, and this other vertical asymptote over here at y equals 0. And we were going to 0 as we were going to negative infinity, so we're going to reach down here, and then we were going to 1 as we were going to positive infinity, and this ends up looking something like this. All right. It looks very, very similar to an arctan function, all right? Anywho, Next example. Where am I at? F, G, right, so H. H. Let's say that I have the limit as x goes to infinity of sine of x. Let's think about this one. As x goes to infinity of sine. Sine is a wave function that looks like this, right? And it just gets repeated forever and ever. It doesn't actually have a horizontal asymptote. So this limit does not exist because it's oscillating. Since sine of x oscillates, right? It keeps oscillating forever and ever and ever. So it doesn't actually get closer to any specific value. It just goes back and forth between -1 and 1, reaching all the values in the middle. But let's look at the following. Let's say the limit as x goes to infinity of sine of x over x. All right, the limit as x goes to infinity. So first, I'm going to do this the incorrect way, all right? And I want to do the wrong way so that you see what not to do. Limit as x goes to infinity of sine of x over x equals 1, right? Sine of x over x is 1. Except this is wrong. And why is that wrong? Because the rule there was not about limit going to infinity. The rule was the limit as x goes to 0 of sine of x over x. That one goes to 1, not as x goes to infinity, right? So it's important that we look at that we take that we keep in mind what x is going to, all right? So that's the wrong thing to do. So what's the right thing to do? Let's see. So now let's do the correct thing. Well, in here, consider the following. All right. So consider that sine of x is bounded between -1 and 1. All right. Sine of x is always between -1 and 1. This tells us that if I divide by x, -1 over x is less than sine of x over x is less than 1 over x. All right. If I take the limit as x goes to infinity of each of these, I forgot to write the limit here. So I'm taking the limit as x goes to infinity of all of these. Well, what ends up happening is that the limit on the left here, this goes to 0. The limit on the right here, this goes to 0. So essentially what we have here is that 0 is less than the limit as x goes to infinity of sine of x over x, which is less than or equal to 0. Well, in here, this should remind you of something. This is called the sandwich theorem or the squeeze theorem, right? The squeeze theorem. So in here, what we can say there is that by the squeeze theorem, the limit as x goes to infinity of sine of x over x is 0, all right? And this actually holds true as well for if x were going to negative infinity. So I'll make that as a note here. Note, the limit as x goes to negative infinity of sine of x over x is also equal to 0. And in fact, let's look at what this function is, right? This is what it looks like. something like this, where it's a wave, but the waves are getting smaller and smaller each time. All right. As we get further away from the y-axis in both directions. Right, so we do end up with a horizontal asymptote of 0 on either end. All right, now, next one. Let's say so that was, I don't know what, E? I, sorry. I couldn't read my own handwriting. I. All right, so J. Let's say that I have the limit as x approaches infinity of 1 over 2x plus sine of x. All right. Well, again here, if I let x go to infinity, well, sine is going to be just oscillating. So we can't just do it like that. We can't rely on an oscillating behavior to figure out what's going on. So we're going to multiply by 1 here. And that one is going to again be based on the power of x that we have there. So I'm going to say if I multiply by 1 over x over 1 over x, well, what do I end up with here? I get the limit as x approaches infinity of 1 over x over 2 plus sine of x over x. And now we can see what this limit's doing. This right here is going to go to 0. This right here is going to go to 0. So we end up with 0 over 2 plus 0, which is just 0, right? And that's a 2. Okay. Let's say that we have the limit as x approaches infinity of ln of x squared plus 1 minus ln of x squared. So in here, if I just plugged in infinity, well, I end up with infinity minus infinity. And even if I rewrote this, right, like say, for example, instead of having that x squared, I have a minus 2 ln of x. That doesn't change anything, right? As x is going to infinity, this is ln of infinity, it's infinity. 2 ln of infinity, still infinity, because ln looks like that, right? And it just keeps getting bigger and bigger and bigger. But what we can do here is apply some rules of ln, and we can say here now that we get the limit as x goes to infinity of ln of, and I'll do it in one step here, x squared plus 1 over x squared. And at that point, well, I still can't really do anything because infinity over infinity inside here is not helpful. So I end up with the limit as x goes to infinity of ln of, this can be rewritten as 1 plus 1 over x. And at that point, as x goes to infinity, this right here goes to 0. And then we have 1 plus 0 is 1. So we end up here with ln of 1. But ln of 1 is 0. So we actually have a horizontal asymptote of 0 there, right? And in the first quadrant, this looks like this, essentially. Right? In fact, it also looks very similar on the other quadrant. That's essentially what we've got there, where, there we go. Now, next example. And I'm on, where am I at? Okay, so L. Let's say that we have the limit as t goes to infinity of 8t to the negative 1 minus arctan of t. Alright. And here, the very first thing I'm going to do is I'm going to rewrite this. I don't like that negative exponent, so we're going to have the limit as t goes to infinity of 8 over t minus arctan of t. As x goes to infinity, 8 over t, excuse me, as t goes to infinity, 8 over t goes to 0. But what about arctan? What is arctan doing? Well, let's see what that function looks like for a second. The arctan function has two horizontal asymptotes, and it looks as follows. Right? That's arctan of x, or of t in this case. This horizontal asymptote on top is where y is equal to pi over 2, and this one is where y is equal to negative pi over 2. So as t goes to infinity, arctan goes to pi over 2. So perhaps I should say here this is f of x equals arctan of x. So arctan is going to pi over 2. So what we get now here in this limit is the limit as t goes to, well, we're already taking the limit. So 0 minus pi over 2, giving us negative pi over 2. Right? Next example. So that was L. M. Let's say that I have the limit as x goes to infinity of x to the fifth. Well, in here, as x goes to infinity of x to the fifth, well, that's infinity to the fifth. That's infinity, so does not exist. Similarly, if I take the limit as x goes to negative infinity of x to the fifth, well, that's going to give me just negative infinity. Still does not exist. What is this telling us? Well, this is just a polynomial, right? X to the fifth. And it should make sense that we don't have a horizontal asymptote with polynomials. In fact, polynomials overall don't have horizontal asymptotes. This is essentially what that function looks like. F of x equals x to the fifth. No horizontal asymptote on either direction. All right. So in general, that is true of polynomials. Um, not to be confused with rational functions, right? All right. So that's n. So let's say that I had the limit as x goes to infinity of 2x squared minus 4x over x plus 1. All right. Now in here, we already know how to find this limit, right? This is going to infinity. In other words, it does not exist. And how do I know that? The degree on top is bigger than the degree on bottom. We're going towards positive infinity. It's all going to go to infinity. Okay. But what else can we get out of this? Well, let's see. Let's see what we can do if we rewrite this. And I'm going to do long division. So let's rewrite this using long division. So x plus 1 into 2x squared minus 4x. All right. Now in here, if we do this division, well, x goes into 2x squared 2x times, so we get 2x squared minus 2x, subtract 2x squared minus 2x squared goes away, negative 4x minus negative 2x squared is negative 2x. At that point, to go from x to negative 2x, multiply by negative 2, right? And we end up with here negative 2 times x is negative 2x. Oh, sorry. Look at that. Mistake. 2x times 1 is positive 2x, making this a negative 6x. Oh, negative 6x. Alright, then negative 2 times x, we end up with negative 2x. Negative 2 times 1 is negative 2. But it's not negative 2. Oh, look at that. That was horrible. I caught my mistake and then I made it even worse. I gotta multiply by -6. There we go. -6 times x is -6x, and then -6 times 1 is -6. Subtract. Well, here there's an invisible plus 0, right? -6x minus -6x, that goes away. 0 minus -6 is +6. So what we found here, well, what did we find? We found that 2x squared minus 4x over x plus 1 is equal to 2x minus 6 plus 6 over x plus 1. So what we can say now is that this limit becomes the limit as x goes to infinity of 2x minus 6 plus 6 over x plus 1. Notice here that this goes to 0. And as x gets bigger and bigger, this piece, this little fraction, it matters less and less and less, and the overall value is being decided by this piece over here, 2x minus 6. This is called a slant asymptote, all right? This 2x minus 6 is going to be a slant asymptote. And what do I mean by that? Let's look at the graph of this function. Um, it looks something like this. We've got a slant asymptote of 2x minus 6, which is something like this, right? Um, y equals 2x minus 6. We've got a vertical asymptote at x equals -1. Um, that's at -1. And the function looks like this. Right? Notice that, well, as x gets bigger this way, we're going to get closer and closer to this um, slant asymptote. Similarly, this way, all right, we end up closer and closer to this because overall, this 2x minus 6 is really again deciding the value of the function. All right. So let's do another one like this. And then we'll talk about how to tell when this would happen. So example P. No, not P. Am I at P? Yeah, P. Okay. So let's say that I have the limit as x goes to infinity of 6x cubed minus x squared plus 3x over 2x squared plus x. All right, and here again we know how to find this limit. Overall, it's actually infinity. Why do I know that? The degree on top is bigger than the degree on bottom, and x is going to positive infinity, so overall it's going to infinity, so there's no horizontal asymptote. But let's see what happens here. We can rewrite this in the following way. Um, the bottom can be factored to be x times 2x plus 1, and the numerator can be factored to be x times 6x squared minus x plus 3. In here, these x's right there get canceled out. What was that called when we canceled out something like that in the limit? Well, before I continue, I will remind you what this actually is telling us. This is telling us that there is a removable discontinuity at x equals 0, right? Because we were able to cancel that out. We were able to essentially remove it from our fraction here. All right, so what do we end up with now? Let's see. We've got the limit as x goes to infinity of 6x squared minus x plus 3 over 2x plus 1. All right, now in here, I'm going to do long division again. 2x plus 1 into 6x squared minus x plus 3. And we say, well, to go from 2x into 6x squared, we multiply by 3x. So 6x squared plus 3x, subtract. 6x squared minus 6x squared goes away. Negative 1x minus 3x is negative 4x. And now to go from 2x to negative 4x, multiply by negative 2. Negative 2 times 2x is negative 4x. Negative 2 times 1 is negative 2. Subtract 5. So what this tells me now is that this fraction, 6x squared minus x plus 3 over 2x plus 1, is equal to 3x minus 2 plus 5 over 2x plus 1. Right? And now, in here, this is the overall driving force, right? So this will, as we take the limit as x goes to infinity, we end up with 3x minus 2 plus 5 over 2x plus 1, right? And in here, this fraction here, that ends up going to 0. So this is the overall driving force of the function. Now let's see what this one looks like. This one, in fact, looks very, very similar to the last example, with one small difference. We've also got a vertical asymptote. This one happens at negative 1/2. We've also got a slant asymptote, something like that, right? Where this is the line y equals 3x minus 2, right? That's what we were left with here, the slant asymptote. And our function looks like this. This piece down here just goes like that. But this piece over here looks like this. Right? Something like that. Where we have an open circle here, and it's not filled in at all. So we have an open circle there. Right? And there you go. That's what that looks like. But the difference here is this one actually has that hole there, right? That's that the removal discontinuity that we were talking about, that I mentioned up here at x equals 0. All right. Now, as far as what value would that be? Well, take the limit as x goes to 0 of this stuff, we get 3 over 1. So it's at the height of 3. All right. The height of 3. All right. So that is the end of 4.5. Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.